पीछे से आओ ये माइक है ना देख
So, welcome back. So now let's move ahead. So we have the next speaker, Dr. Janshar Yadav from Allahabad University. So he will talk about the
तो यूनिवर्सिटी से
multi-resolution
बात
analysis and construction of
इलाहाबाद
matrix.
यूनिवर्सिटी
So now Dr. Yadav is currently working
क्या
as
कोई
an
बोतल
assistant
है कोई
professor in
बोतल
Department of Mathematics, University of Allahabad, Prayagraj. He did his BSc, MSc and PhD from the same university. He completed his PhD in gradient analysis. His areas of research includes gradient analysis, harmonic analysis, and
देख लो
sampling
इधर से
theory.
देख लो
Earlier, he served as an assistant professor in IIT Kurukshetra. So now,
ठीक है
to welcome the speaker, I would like to invite Dr. Sweta Kumari, Assistant Professor, Electrical Engineering Department from Government Engineering College, Siwan.
टाइम नहीं है तो इंट्रोड्यूस के एक और मरी
चल रहा है लाइन में
Yeah, thank you. So now I would like to invite the Professor Gyanchand Yadav for his lecture. So now the floor is yours.
So first of all, I thank the organizer for giving me this opportunity to talk with you. So the title of my talk is Multi-Resolution Analysis and the Construction of Wavelets. So wavelets, as you know, that it is about 3 decades old subject, and it was first evolved by experiment done by Moller, who was an engineer and he was geophysicist. So his main work was to identify the material inside the Earth's surface. So the procedure they used is they create a acoustic waves at the surface, and then wave goes inside, and then from there it reflected. So they study the frequency component, and from that they conclude that what material could be inside the Earth. So for this study, earlier they used Gabor technique to identify, to study the frequency, reflected frequency. But in Gabor, as we discussed, that there are some limitations, so it was not very useful for him. So he developed his own technique to identify the material, and later he takes shapes of wavelets with the help of some mathematicians. So from there it evolves, and it is around 1982 around it happens, and then 1998 Malat and Mayer gives the concept of multi-resolution analysis, and from there it evolves very much, and then now it is applicable in almost all area of science. So everyone is using this wavelet. So in my talk, I will use some definitions which I think you know, you are familiar with that, and that is Fourier transform and inverse Fourier transform. So I will write the definition and then I will. So for Fourier transform, I will use the following definition. So if f is a function, suppose f is a function in L1 intersection L2. So for L1 function it is defined, and for L2 function we use the concept of density. So L1 intersection L2 is dense in L2, and from there we extend the definition to the L2 function. So and a Fourier transform. So I will use the following definition of xi is equal to integral over r of x e power minus I x and dx. And for inverse Fourier transform, inverse x is 1 upon और बड़ा तो x
चचा नया चीज लाए
inverse x is 1 upon 2 pi and integral over r f right e power minus f plus I by x. Some other text 1 upon under root 2 pi and 1 upon under root 2 pi. But I will use this definition. In Fourier transform, no constant can involve Fourier transform. And then we have Parseval relations. So inner product of f cat g cat is 2 pi times f pi times inner product of g. And then we have a Fourier emergent formula. Fourier emergent. So fx is 1 upon 2 pi integral f at z e power I the x. So basically it is after calculating Fourier transform, you can get back to the original function of x by this formula. So it is inverse of f cat. So f cat inverse. So f cat inverse. F cat inverse is your function f. So for L1 function, there are conditions. So if f is in L1 and its Fourier transform is also in L1, then you can get this formula. For L2 function, you can also get this formula. Okay, so as you know that Fourier transform, it has many applications, but it has some deficiency also. For example, it gives the frequency component, but the time information is missing. So at what time that frequency is occurring is not known. And second, it is well suited for this stationary signals, but if you have transient signals, then it is not as good. Transient means the frequency is changing in very small duration of time, changing very small duration of time. Okay. Also, it involves whole integral. So suppose you want to calculate the Fourier transform at a single point. So for that also you have to integrate the function over whole real time. So it takes large amount of time to evaluate the frequency at a single point. So these are some deficiencies. So to overcome this deficiency, windowed Fourier transform was proposed. So in windowed Fourier transform, we take a window function. So window function means in a small duration of time it has value and otherwise it is zero. So for example, take a this rectangle function, something like this, or some Gaussian function. So Gaussian function e power minus x squared by 2, this function, so it has that like this. So in a small duration of time, this function has value, otherwise it is 0. And what we do, we shift this window and multiply it. So actually this integral becomes integral over fx, and then suppose w, this is your w function, over w, and x minus tau, and then e power minus I. So what we are doing, we are cutting the signal, x as value, but when we multiply it with a window function, it has only value in that region. For the region, it becomes 0. And then we evaluate it. So at a specific time, we get the information about the function. So it reduces, and so it has some advantage over the Fourier transform. And motivated by this, a mathematician called is known as Gaba. He proposed a basis known as Gaba basis, and he took this function G family, and Gmn is defined by, so G is a function, alpha function. G is an alpha function, and Gmn is defined by e power 2 pi I mx. So again, we take some function like window function G, and then shift it and then modulate it. So it is combination of shifting and modulation. So with the help of this, he tried to create a basis for L2 function. So it got some advantage over this Fourier transform, and actually Morlet was with the help of this Gabor basis. He was trying to find these regions. But later, and one disadvantage of this is that this window is fixed in some sense, means it is rigid. So if it is this, then it is this. And if you have very short signal in a very small duration of time, then you cannot cut this window, means it is fixed. And wavelet, what wavelet do? It gives you the reflexivity to contract this window also. So in place of modulation, we use dilation here. So by using dilation, we can contract and expand this window also. So that is the advantage over this type of basis. So then it becomes, wavelet becomes, due to that flexibility, it becomes more useful. So GMN this, and one result which provides uncertainty about the use of this type of basis. So this result shows that if you are using this basis, then either you can confine in time domain or you can confine in frequency domain. So simultaneously you cannot work in both the domains. So that is a result. That result is called value in your column. If GMN is a basis, GMN is defined basis, M and N are integers. So if it is a basis, then either this happens, integral over R, x square mod x square mod dx square dx is infinity or integral over R xi square mod of eta xi square dxi. This is so both cannot be finite. Either in time domain it is flow of infinity or in frequency domain it is flow. So this is some kind of uncertainty, and due to this result it is not much used later. So you cannot confine in both of the domains. So this is the result, and I will sketch the outline of this proof also. So to prove, we define two operators, and then we will show that both operators cannot in L2. So both operators cannot in L2 function. Yes, so I'm defining two operators, Q and P. So Q is an operator which is defined this way. Q of dx is x dx, and P of dx is minus I and d dash. So then what will be integral of Q to x? So this is your first integral, integral x square mod of dx square, and the second px mod of p dx is actually integral over mod of g dash x square dx. And from G dash we go to the Fourier side. So for Fourier side we use that result. inner product of f cat g cat. So it will give norm of f cat, norm of f cat square is 2 pi times norm of f square. So that is norm of f square. So from there we get 1 upon 2 pi integral norm of g dash cat xi square dz. And the Fourier transform of derivative of function. This you have evaluated already. So what you do, just integrate by part. So first part will be 0 and the second part will be xi times d by xi. This is simply integral over r and xi square mod of g cat. So my statement is, and these two numbers cannot be finite. So either one is infinite or can be infinite. So you will see that in terms of Q and G, we will prove that both cannot be finite. Means both cannot be L2 function. So if suppose this is L2, then this will be less than infinity, this also will be less than infinity. So both cannot be L2 function. So proof is by contradiction. So we assume that both are L2 function, and then we will get some contradiction. So we suppose that both Q and P are in L2. So if this is in L2, then we can calculate its inner product. So inner product of this, and we have assumed that GMN is a basis for L2. GMN is a basis for L2. So if it is basis for L2, then any element can be written as linear combination of these terms. So I will write Q to the linear combination of this UG, GMN, product, GMN, G. Okay, writing QG as QG, GMN. So sum is over M and L. Because it is a basis. Now use the linearity. So take this term outside. So this first term is QG GMN. Then you get this summation and QG GMN and then GMN P. Now evaluate both terms separately. First evaluate this term and then find this value of this term and put here. So the first term is QGGMN. And this, I am writing it like this. QGGMN minus n times GGMN. Why like this? Because the last term is always 0. And times G, GMN is always 0. Because GMN is basis, G is actually your G00. So for M non-zero and N non-zero, this inner product is always 0. It has only value when M is 0 and N is 0. And when N is 0, I am multiplying with N. So this term is always 0. So I am subtracting 0 comes from there. And now then combine this. So you will get QG minus NG, the product GMN. Now apply the definition of QG. So a little bit calculation by doing. So I am not going to the detail of that calculation. And you can verify this. Finally, you will get that this term comes out to be and G minus M with QG. Inner product. QG GMN is same as G minus M in And similarly, the second term, evaluate GMN PG, again apply the similar type of argument, and you can show that GMN PG is same as PG G minus M minus. Okay. So put this value here. So QG GMN, this equation QG PG. This inner product will be, this is QG GMN, so same as G minus M minus N and QG, and this term will be second term PG G minus M minus N. But you are running over integer value. M is integer and N is also integer. So if M belongs to Z, minus M is also there. Okay. So this total terms you can verify it same as PG. So on the one hand, you will get that this inner product is equal to that, and second, we calculate this inner product by applying the definition of it. So just apply the definition of inner product and QGPG same as integral QG, that's dx, and PG is minus I times d dash x, and R dx. So inner product of Fg is Fg bar. And now evaluate this term. So again, multiply, then integrate by part. So finally, you will see that this value comes out to be minus I times inner product of Dg with Dg. And from where you will get contradiction that inner product Gg is always 1. So minus I times Gg Qg. So on the one hand you are getting this, on the other hand you are getting this. So it is not possible. So it means your assumption is wrong. Means Qg and Pg cannot be both in L. Means one is infinite. So either one is infinite or second. So I will illustrate this with the help of two examples. So take first example and take this function. So example and take G. Characteristic function on 0, 1. So if you take this G, G equal to this, then you can prove that GMN, which we have defined earlier, it is an orthonormal basis for L to R. And for this value, integral of x squared, gx squared, not gx squared, it is finite because value is only 0. So first integral is finite. But second integral will be infinite because when you evaluate its Fourier transform, you will get sinc function. And that was all over the R. So that terms will be infinite. So with Fourier transform, you can verify that g cat xi, and this value is e power minus I xi by 2, and sinc function. Right. So when you take mod and then multiply by xi square and you can integrate, that this will become infinite. So first is finite, while the second integral is infinite. And second function, if you take this value, second, and gx, suppose I am taking this sinc function, so sin pi x upon pi x. Then again you can prove that it is also an orthonormal basis for L to R. And in this case, first integral is infinite, x square gx square, the sinc function infinite. So you cannot get both values to be finite. And to remove this difficulty, the concept of wavelet arises. So the definition of wavelet, so there are two definitions, one is in continuous frame, second one is in discrete frame. So I will use discrete frame, and the dilation I am taking 2, that's why it is called also Dyadic wavelet. So definition. So if psi is then your L2 function, then I am defining psi jk a family X 2 power j by 2, sorry, 2 power jx minus. So in place of modulation, we have taken dilation. And j and k are integers. So this 2 power jx, this contracts, suppose you got a function, for example, I am taking this side, minus 1. Suppose I this side. So its value is between minus 1 and the dash 0. So what will be psi of 2x? So the support of psi of 2x will be contracted. It will be minus half and half. So it's minus half and half. Minus half. Suppose I am taking psi 2 square x. So again, support is contracting. So as long as it is increase j, the support will be contracted. If you take negative j, psi x by 2, then psi x by 2 will have support minus 2 to 2. If you take x by 2 square, then again 100. So it means this dilation factor gives you freedom of contracting and expanding the function. And according to your needs, you can take either contraction or expansion of the same function. So basically, wavelet is a function, one function, and with the help of dilation and translation of this function, we generate a basis of L2R. So one function and its it generates, if this is the case, then we call psi to be orthonormal. So if psi jk is a basis, then we call psi to be basis. And some book write it mother wavelet because from psi we are getting so many functions, familiar functions. So this is also called dynamic wavelet because the dilation factor I am taking 2. And there are continuous analog also. So for AB continuous, you can define psi of AB. Okay, so this is the function, and the well-known example you have heard, that is Haar wavelet. Haar wavelet. Haar wavelet is a function, and this 0 to half it is 1 by 2. One and a half to 1 is minus. So Haar proposed this function in 1909. So at the time, wavelet word was not known. So Haar was just trying to generate a basis with the help of this function only. So he was taking psi and then contracting and dilating. And the second factor is translation. You know that this is dilation and this is translation. So if I take psi x minus 1, x minus 2, x minus k, so it will translate along x-axis according to the sign of t. So with the help of single function, Haar tried to generate a basis for L2R. So that is an earlier example of wavelet you can say. This proposed in 1909, and wavelet word was not used. And there are many more examples. So second one is Shannon wavelet, and there are Jones wavelet. So if time permits, I will explain a wavelet called Shannon wavelet. But I will come to my topic, and the topic is multi-resolution analysis and perception of wavelet. So multi-resolution analysis concept was proposed by multi-resolution analysis. It was proposed by Malat and Mayer around 1988. And this is a very useful method to obtain a wavelet. So whenever you have an MRA, you can always construct a wavelet from that MRA. So this definition, you know, this satisfies 5 conditions. Vj agar Vj is closed subspaces in I2R, so Vj are closed subspaces of I2R. Then it satisfies this 5 condition. First one is nested. Second one is agar if F is invisible, and if and only if it's 2 dialects is invisible plus 1. Third one is it's about its intersection. Singleton 0. Fourth one is it's about union. It dams in L2R. And fifth condition is there is a function phi in V0 such that it translates phi dot minus k, and k is the integer. There is a function phi such that this forms an orthonormal basis. And sometimes this phi is also called the scaling function. So whenever you have an MRA, you can always get that wavelet. So, okay, so let me give you one example. So there are certain results, and the first one is that these are not all independent. So suppose you have the condition first, second, and fifth, then always you can say that this implies the third condition. First, second, and fourth will always imply third condition. And for union also, you can do a result that if your phi cat 0, phi cat 0 means this Fourier transform of this scaling function. Phi cat 0, if it is non-zero, then it is equivalent that union Vj is dense. These are the two results. So first result is which explains that condition first, second, and fifth. This always implies third condition. And second is the condition first, second, fourth with this condition, phi cut 0 is non-zero. Then always you can show that union is dense. Okay, so I am not going to prove this result. I want to explain one example of this MRA. So, and then if time permits, I will prove this result. Because organizer told me that many participants are from the engineering background, so they do not like to prove many results. They just want the simple things and their applications are. So first, let me prove one example. So one example of an MRA. So in MRA, I need a closed subspaces of L2, Vj. So I have to define a closed subspaces Vj, and then I have to show that this satisfies all this phi property. So I am defining a Vj. So my Vj is F L2 such that F is constant. F is constant on interval 2 power minus j k, and then 2 power minus j k plus 1. So k is integer and j is also integer, so j is 6. So take this as an reason. So have those functions which are constant term and this type of interval 2 power minus jk and 2 power minus j k plus 1. So what will be your v0? V0 will be the solution of those functions which are constant on the interval of the type k plus 1. So 0, 1, 1, 2, 2, 3. On this interval, it is a constant function. It may be discontinuous at endpoints. So 0, 1, 2, 3, it may be discontinuous. So constant value may be different. Okay, so first condition you have to show that Vj is contained in Vj plus 1. So if your function is constant on Vj, so if you take Vj plus 1, then the power will be minus j minus 1. Means the interval will be contracted. So if f is constant on Vj, then automatically it will be constant on the next interval. So f will be the constant on the next level, Vj plus 1. And suppose f is, second condition, f is in Vj. F is in Vj. Then what will be f2 dot? F2 dot. So f2 dot means f2x. So f2x will be constant when 2x will belong to this interval. And if 2x belongs to this interval, then x belongs to 2 power minus j minus 1 we will get. So f2j will go in Vj plus 1. That is in Vj, then f2 dot will be constant on 1 upon 2 times that interval. That is the function in Vj. And third condition, intersection. So intersection of all Vj's will be 0. So take a function f in intersection of all Vj's. If f is in intersection, means f is in Vj for every Vj. Okay. So in particular, if I take k equal to 0, then I will get the interval 0 and 2 power minus j. And when I take interval k equal to minus 1, then I will get interval minus r 2 power minus j and 0. Okay. So take k equal to 0. So 0 to power minus j, and you take k equal to minus 1, minus 2 to power j, and 0. So f is, if f is in intersection of Vj, then f is in Vj for every z. So for every z, f is constant on this type of interval. Okay. Now take j tending to minus infinity. J tending to minus infinity. So this 2 to power j will go to infinity. This 2 to power minus j will go to minus infinity, and function is constant on f is constant on 0 to infinity, and from second you will get that minus infinity. And the only function which is constant on whole real line and it belongs to L2 is a 0 function. Any non-constant function cannot belong to it. So the only 0 function will remain in the intersection of these. The fourth property, union. So union, to show that union of Vj is not easy every time. So generally we use that characterization that union is dense in L2. If and only you can show that phi category is not. So you define a phi function such that phi translates a phi form in orthonormal basis, and then so that it is non-zero at 0. Then the first condition will be fulfilled. So I am going to define a scaling function for this MRM, and I will take this function as a scaling function. So phi x and this is your 1. When I take 0 x 1, one side I can go like it okay. Less than 1 and 0 otherwise. So basically in V0 we have a function which is constant on this. So for V0 we have a function which is constant in the interval of the form k plus 1. So I am taking the constant value 1 in 0 1 and 0 otherwise. So when you translate this function, so by the construction, I got my so by the construction, this set is orthonormal because if you take two different elements, so their support will be different. So no intersection part, so it is automatically 0. And the product is always 0. And if you take same, then it's not 0. So by the construction, it is an orthonormal set. And for any f in V0, for any f in V0, you can write fx. Fx equal to ck by f. Where ck is the value of the function at k plus 1. So I am translating this function. So this function will be 1 interval on interval k plus 1 and ck is that value with So since f is constant, so f will take some value at that interval. So that value I am giving in ck. So ck is the value at that multiplied. So this always generates any function in V0 and the coefficient ck, you know that in this case, this summation of this coefficients are always less than norm of f. Always less than. Sorry, equal to not equal to normal. And f is 0 in negative, so normal f is finite, so this sum is finite. So any f in V0 we can always express in this way. So this construction, which we have, okay, and the last one is phi at 0. So phi at 0 you can show that it is 1. Take this function phi, evaluate its Fourier transform and put the equal to 0. So you can show that phi at 0 it is non-zero. So if it is non-zero, then the condition for the union is there. So this is an MRI. So by the defining suitable PZ, we have constructed a multi-resolution analysis. And one more example I have. So it may be exercise for you. So second, you can show this. Suppose I am taking this region L2 so that support of FL is contained in minus 2 to the power j pi and 2 to the power j. If you define these like this, then again you can prove that it is also an MRI. And it is exercise for you. So you have to do some mathematics because it is defined in terms of Fourier transform. So for function, you have to be careful. So this is again an MRI. So these are the two examples of multi-resolution analysis. And how you construct a wavelet from a given MRI. So whenever you have MRI, you can always get a wavelet. And the first example which I illustrated, this is also known as RMRI. So this is also known as RMRI. Because from this MRI you will get wavelet as this RMRI. So I will come to the construction of an orthonormal wavelet from a given multi-resolution analysis. Okay, so condition gives that Vj is contained in Vj plus 1. So construction. So how you will construct the wavelet from again? Okay, so the first condition gives you that Vj is contained in Vj plus 1. So this is like nested subspace. This is your Vj, then this is your Vj plus 1. And Vj plus 1 is nested in Vj plus 2. And Vj minus 1 is inside this Vj. So take the orthogonal complement of Vj. So this is your Vj. Now take the orthogonal complement, which is remaining in Vj plus 2. So call it W. So I am calling it W. So I can write Vj plus 1 to be direct sum of Vj and W. Vj, I can write it like this. Vj plus 1 is Vj direct sum W. Now, as Vj goes to j tending to minus infinity. So what I did, I am writing it. Vj minus Vj. Vj I am writing it like this. Vj minus 1 direct sum W. J minus 1 direct sum Wj. Then again continue this process. Vj minus 2 is again direct sum of Vj minus 1. So it is direct sum of Vj minus 2 and Wj minus 2. Now as j decreases, the third condition shows that f goes to 0. So in the intersection part, nothing decreases. So as j decreases, only Wj remains. So this will be the direct sum of W L. L is from minus infinity to this j. And the fourth condition is as you increase this j, so when j tending to and j becomes larger, this Vj tends to L2 function, L2R function. So when I increase j, I will get L2. So the L2R finally becomes the direct sums of these spaces and this. So we have decomposed as L2 in Wj spaces. Okay. So to get a basis for L2, it is enough to get basis for Wl. Okay. And since okay, and the second condition and this condition. If f is in Vj, then it's two direct in Vj plus 1. Similar type of condition holds for Wj. So if f is in Wj, then its two direct will be in Wj plus 1. Okay. So it is again enough to find one W. So it is enough to find one W. Okay. So suppose you get W0. So if you get characterization for W0, then always you will get a basis for n. Because from W0 with two directs you can go to any WL, then take their unions, so it will be a basis for n. So this is the procedure to construct a wavelet for L2R. So the whole task is to find W0. So find the characterization for W0. So means what type of functions are in W0. Okay, so we start with V0 space. So start with V0 space. And V0 space is direct sum of V minus 1 and W minus 1. So the V minus 1 is contained in V0 and the orthogonal complement of V minus 1 is W. So V0 is direct sum of V minus 1 and W minus 1. And you know a basis for V0, 5, so fixed condition. translate of phi is a basis for V0. So phi function in V0. Okay, now apply the dilation property. If phi is in V0, then it's minus 1 to power minus 1. It will be always in V minus 1 by the second condition of from V0 to V minus 1, you will get x by 2. Okay. So it is in V minus 1, also it is a vector space, so any constant scalar multiple is also in V minus 1. So this function is V minus 1. And V minus 1 is again in V0. Is again in V0. And you have basis for V0. It means this function is in V0 and V0 has a basis. So this is linear combination of those elements. So 1 by 2 pi x by 2. 1 by 2 pi x by 2 is a linear combination of alpha k pi x plus k. And what will be alpha k? This is linear product of and pi. So this element can be written as linear combination of elements of basis of this. And the second thing is, okay. So this is your equation. Now calculate Fourier transform. So you can verify that the Fourier transform of 1 by 2 pi x by 2. This is so not x dot pi dot by 2. Its Fourier transform might be calculated this also. Just change of variables. X by 2 को keep or just करिए formula you will get this. So the Fourier transform of this is phi cap 2 xi and the Fourier transform of phi x plus k. So if you have a translation in function, then Fourier side you will get modulation, exponential factors. So apply procedure. So from Fourier transform you will get phi cap 2 xi. This is summation alpha k e power I xi k and phi k. Fourier transform of this and Fourier transform of x plus k is e power I xi k and phi k. So this term I will call it as symbol and 0 xi, and this term is known as low pass filter. So in filter theory, actually this subject arises in engineering subject. So engineering people use this term low pass filter, and then you will get high pass filter. So the same here. So it is something like which separate the frequency component. So low pass filter means that it allows to pass the low frequency component and the high frequency component. Similarly, high pass filter allows to pass high frequency component and be constant to start lower frequencies. So from there this works on. So I will call this low pass filter, and okay, and you can verify that it is a 2 pi period function. So in place of xi, if you place xi plus 2 pi, you will get the same. So N0 xi is a 2 pi periodic function, so it belongs to L2 t instead of minus 5 pi. Okay. Now, so we got this formula. So I will use this pi cat to xi and 0 xi pi cat. But and then there are some more results which again I am not going to prove, might we have proved this result also. So this, all these results will be used to find function in the procedure. So the first result which I am going to put here is that if G is an L2 function such that G dot minus K is an orthonormal system, then we have factorization that mod of G cat is I plus 2k pi mod square is 1. Okay. I think Professor Vera has proved this result. And the proof is very simple. Okay, so this is useful because you have taken the same thing in fifth condition of an array. So translates of pi or orthonormal basis. So always you have to use the orthonormal thing. So if it is an orthonormal, then this value is always 1. And simple proof, just take the inner product of B with any its digit. So this has only value when k equal to 0. For non-zero k, it is 0, because it is an orthonormal system. Now, apply the parsimilization. So it is 1 upon 2 times, 1 upon 2 pi times G cat and Fourier transform of this. Fourier transform of this will come with the exponential factor, then use the Fourier basis expansion of the function and you will get the sequence. So I'm not going to prove this one. And second result which I will use. So I am just illustrating the results which we use to prove and proof is not, some proof is easy, but some proof are not easy. Second result. Suppose G dot minus K is Z. Second result. It is an orthonormal system. It is an orthonormal system. Then mod of support of G cat is always given. So if translates are an orthonormal system, then support of Fourier transform of G cat, it cannot be less than 2 pi. Either it is equal to 2 pi or it is always greater than 2. And if it is equal to 2 pi, so minimum case when it will be equal to 2 pi. Then the shape of G is known. So G will be a characteristic function on K where measure of K is simple. So the least case, when suppose is exactly 2 pi, the form of G will be always characteristic function on set K where K has measure 2 pi. And since this has minimum support, the wavelet which arises like this has a name in literature and that is called no. So such type of wavelet in literature they are called minimally supported frequency because its Fourier transform has minimum support 2 pi. Okay. So minimally supported frequency, and the second example which I have not proved, that is Sinus wavelet. Sinus wavelet is an example of NSF wavelet. So this is second result, and then third result is for low pass filter. So this also might be seeing this result, and mod of M0 xi mod square plus mod of M0 xi plus pi, this mod square is also true. So the low pass filter satisfies this condition. So I'm just illustrating the results only. And then, okay. So my task is to find double zero. So this is your call it v minus 1, and v minus 1 is contained in v0, and its orthogonal complement is w minus. So v0 is direct sum of v minus 1 and w minus 1. So first I will characterize the function which are in v0, then I will characterize the function which are in v minus 1, and then I will characterize the function which are in w minus 1. And if you get the characterization for w minus 1, then always you will get characterization for w0. That is your main. So the characterization for v0 and v minus 1 is the following. So this is your next result. That v minus 1, this is the function such that f cat xi equal to m2 xi and 0 xi and phi cat xi. And v0 is those functions whose Fourier transform is L by phi cat xi. So second proof is easy. First proof we have to do a little bit calculation, and we can show that the function which are in v minus 1, which they always this type of form, and m0 is your low pass filter, phi is your saving function, and m is a 2 pi periodic function in n. Similarly, here L is again a 2 pi periodic function in n2, and phi is your saving. So the w minus 1 space is in v0. So if it is in v0, means it has this form, but it is perpendicular to v minus 1. So if it is perpendicular to v minus 1, then you can show that the two functions which are perpendicular to these spaces is equivalent to find that these two are perpendicular. The coefficients. This we can prove. So by taking Lxi perpendicular to m2 xi phi cat xi. So in perpendicular means inner product is 0. And then do the calculations. So you will find a precise form for L. So L, the form of L comes out to be this one. The form of L comes out to be Lxi equal to some mu xi is polarized. So this is depolarized, and mu of 2 xi and 0 xi plus pi bar and pi cat. This we can do. So this proof is not easy. So you have to do a lot of calculations to do this. So if I get a form for L, then I will get a form for function in W minus. Because these are the functions which are in V0 but perpendicular to V0. So the final form for W minus 1 space, this will be those L2 functions. So Fourier transform is always more. F cat xi is depolarized, so the same thing. So let's say depolarized xi, xi, and 0, not less than 0. And 0. bar and pi. So finally you get the characterization for function in W minus 1, and from W minus 1 you will get the characterization for W0 because you have a state. So the state W0, and W0 will have this function. W0 is growth function whose 2y is equal to e power I by into 2y and 0 y plus pi bar and pi. So in W0 we have this type of function. So you can replace 2 xi by xi. So if I replace 2 xi by xi, I will get xi, then xi by 2, xi by 2, xi by 2. So I'm going to write the same thing. Xi by 2. So f at xi is e power I, xi by 2, nu xi, and 0 xi by 2, pi and pi there, and xi by 2. Okay, so now up to now we get the shape of the function in W0. Now the last thing is we have to find a function whose translates form and basis for W, and that is your wavelet. So again you can prove that if psi is this is a wavelet, then mod of nu by this. So if you prove that mod of nu is 1, then this function is a wavelet for n. So this is the whole construction from multi-resolution analysis to wavelet. So and then I will illustrate one example for you. So this is how this works, and that is again R wavelet. So in R wavelet we have defined the space V0. From V0 we calculate, we find the scaling function, and then we find low pass filter, and then finally we will show the shape of the function. So I think we find the 5 minutes. So in next part I will illustrate that example. So these are all results which I will use. I will not prove any results because it will take a lot of time. So just I will illustrate one example using this. Hang it out. And then next also, so actually multi-resolution analysis is a process to get a wavelet. So if you have multi-resolution analysis, then you will always get a wavelet, but not conversing also. I mean, suppose you have a wavelet, then it is not necessarily associated with any multi-resolution analysis. So one example I will show that there is a wavelet which is not associated with any multi-resolution. So one side you will always get, but all wavelets are not necessarily associated with multi-resolution analysis. So that wavelet is known as non-schematic. So if I permit, I will give the example of that also, and then there's a decomposition process. So suppose you have a function, L2 function. So how you will decompose the function into the subspaces V0 and W0 and then the different levels. So that is important because whenever you have a function, you have to ultimately decompose it into different subspaces. So the decomposition of the function, and after that, once you decompose it, again you have to construct the original function with the help of those coefficients. So that is decomposition and reconstruction. So in next lecture I will take it.
Sir, I have a question.
Yes.
Sir, as you mentioned, we need a scaling function for defining an array.
Huh.
There exists 5
whose translation in form of orthonormal basis we have.
Right.
So how to choose that file? Is there any?
No. The selection of file is not an easy. So, for example, the MRI which I illustrated, that is only constant function on the integer in kk plus 1. That is. So, I just take one on that interval and just. But it is not always easy. So, there is one more wavelet called Franklin wavelet. In that, we take V0 to be function which is continuous and linear on kk plus 1. In our case, I have taken only constant function, so it is not continuous. You can take continuous and also linear, means at any point it is continuous. So this again, V0 and then separate to Vj. So again you can do that with the answer, but to get the scaling function. So for this scaling function, it is a big expression for it.
So how to prove that the 5 form is scaling function? Like if we choose any file.
No, choice of phi is not arbitrary.
So we have to choose like constant in that interval.
In that, we have chosen constant because that is all easy. But for this, you cannot choose arbitrary. So you have to apply the techniques. So phi cap 2 xi must be m0 xi phi cap xi, that condition, and the characterization for g0 and b minus 1. That you have to take into account. So in this case, the expression of phi cap is a bit long, and that is known as Franklin. And again, you can generalize this also. So it is only linear. Next, you can take polynomial. So it is polynomial in J. So this is also a class of elements.
Like there are the other wavelets.
Yeah, exactly. Now many wavelets are available, and according to your application, you can choose wavelets. So different wavelets are applicable in different parts. Not one wavelet is applicable. According to your application, you can choose the wavelet. And this MSF wavelet, that is very easy to construct. You just take a set K, measure 2 pi, and to be a wavelet set, some characterization is there. So if two conditions are there. So if W satisfies those two conditions, so again you can get a wavelet. So there are plenty of wavelets.
So for those wavelets, the scaling function is necessary.
See what I told, that every MRI gives you a wavelet, but not every wavelet is associated with an MRI. Exactly. So not for every wavelet there is an MRI. So it is a process to get a wavelet, but not all known wavelet is associated with it. So conversion not. So this is the result you have to prove, because till now you got the shape of the function in W0, but now you have to find a function whose translates from an orthonormal in W0. So if you apply that condition also, from there you will get. So you can prove this. I have to, if you want, I can show you.
One more question. Like you may, as you define HRMRA, 1 and 0. So if we define this HRMRA in 2 dimensions, then we have to choose a rectangle or
No. In 2 dimensions, the construction is not easy. So actually, there a matrix involved. So that is called expansive matrix and those things. So actually, I have not done too much things in 2 dimensions also, but it is not as easy as now. So the matrix concept is there, and then some condition. So your definition of size reduces. In place of 2, you will get determinant of K in that case. And then from there, some construction. So people have done some things in 2 dimension and dimension also. So this, that is Gaussian, right, okay. In frequency domain, but that Gabor system does not form. That window function, Gaussian function does not form a Gabor system. That is localized in time as well in frequency domain, but that Gabor system, Gaussian function does not form.
बंद कर।
Thank you, sir, for the nice lecture. So we will meet after lunch.
नहीं ना उसमें
यहीं पे छोड़ देते हैं, डायरी यहीं पे रहने दो। चार्जर ले लो।
रखेगा उसमें कि नहीं।
बस चलो कौन इधर से आया ना, अगर हम गलती नहीं करना लेकिन आता है तब तो मुझे लगता है देर जैसे कि आराम से अकेले कॉल कौन कहा है?
कौन?
पप्पू सर के साथ। हाँ
सर आप नहीं थे क्या आज?
टोटल कितना आदमी है?
मैं 4 आदमी।
बस वाले कह रहे थे
सर यहीं पे फोटो हो जाएगा, साथ में बैठ के फोटो हो जाएगा, यहीं तो रहिए ना। अब फोटो नहीं, अरे भाई सब आ जाएगा, चलिए ना सर।
फोटो तो ध्यान दे रहा हूँ, ठीक है। हम लोग दे महंगा मोबाइल दे।
हाँ
अरे नहीं, सबसे खराब मांग रहा है, बहुत कम दाम।
आप कह रहे हैं महंगा?
आप खाली महंगा मोबाइल रख दिए हैं।
ये देखें,
मेरे वाला में नहीं आया सेंट्रल।
तो हम देख करके ना भेजते तो बिना देखिए कि
आप लोग वाला में
एक
नहीं
एक और
आया।
भेज दीजिए, नहीं तो फिर वो गुस्सा आ जाएगा। लाइव चल रहा है, लाइव है, लाइव, इसमें से ले लीजिएगा फोटो। हाँ तो चलिए चलिए, अभी नहीं तो फिर भाग जाएंगे सर।
थोड़ा सा पीछे आ जाइए,
पहले वो हो जाए।
ऊपर करके
अरे इसका सेपरेट चीज जो मेन तुम लोग समझते नहीं है। मेन जिसे आप मान लो कि हमको अपना फोटो खींचना होता है, क्या करेंगे, मेरा खींच दो, आओ पहले सब साथ में।
सेम बात, मेरा सिंगल खींचते हैं, इनका सिंगल।
तुम्हारा सिंगल तुमको कौन शादी ब्याह के लिए फोटो देगा?
सही है, वो शादी के लिए लड़की ढूंढ रहे हैं।
हाँ कहेंगे ना कॉल से परेशान हो जाएंगे। कहेंगे रोटियों की लाइन लग जाएगी। क्या होगा?
अरे कौन सी सही मान लो सही चला बेटा गया।
संस्थान में हम लोग जाते हैं